This video will take you through the Year 11 chemistry paper of February 2015, higher tier. You should have your test paper in front of you and also the mark scheme as we work through this. Question number 1 was a simple question about atomic structure. The places where people went wrong in this question was thinking that you had to get this information from the periodic table. If that was the case, quite often in the question it says you may find your data leaflet helpful for this question. But look specifically in the question, it says use your knowledge of atomic structure to complete the table below. So actually you didn't need your periodic table at all. So for atom or ion A, you're asked to complete the mass number. You need to remind yourself that the mass number is the number of protons plus the number of neutrons. So if the number of protons is 3 and the number of neutrons is 3, then the mass number is 3 plus 3, which is equal to 6. Now I know you may have spotted that the number of protons was 3, so thought that this atom was lithium, and so the mass number was 7. That was wrong in this case because we have specifically been given the number of neutrons, which is 3. And remember that the reason this happens is because atoms can exist as isotopes. Isotopes being atoms which have the same atomic number but a different mass number. Or you can think of it as atoms which have the same number of protons but a different number of neutrons. So yes, this is lithium, but it's an isotope of lithium. Okay, the next question, atom B, asks you to work out the number of neutrons. And similarly to us saying that the mass number was the number of protons plus neutrons, then we can work out the neutrons by taking the mass number and subtracting the number of protons. So that gives us 27 minus 13, which is 14 neutrons. Atom or ion C asks us for the number of protons. And again, if the mass number is the total number of protons and neutrons, then we can work out the number of protons by taking the mass number and subtracting the number of neutrons. So in this case, that's 11 minus 6, which is 5 protons. For D, again, we're asked for the mass number, and for E as well. So again, it's a case of just adding the number of protons and the number of neutrons. So for D, it's 11 plus 12, which is 23. For E, it's 17 plus 18, which is 35. Again, for E, some people got that wrong as they wrote 35.5, as they had identified that E was chlorine from the number of protons, and the mass number on the relative atomic mass on the periodic table is 35.5. But that takes into consideration the different isotopes of chlorine, whereas we've got a specific isotope here. Because we know the number of neutrons, then we can add that to the number of protons to get the mass number of this individual atom or ion. The next part of the question was a follow-on from that, using the information from the table. Work out the identity of the atom or the ion, but also the charge, because the question said they may be atoms or ions. Now I do think the question was slightly poorly worded, because it says give the chemical symbol for it. Really they should have said give the chemical formula for each of the particles, because they expected you, if the particle was an ion, they expected you to give the charge. So let's have a look at A. We can get its identity, which most of you did, from the number of protons. Remember, the number of protons never changes. So if you're looking for the identity of an atom, then look to its number of protons. Because it has 3 protons, we can tell it's lithium. But we need to check to see whether the lithium atom has a charge, in which case it would be an ion. It's going to have a charge if the number of protons is different to the number of electrons, because remember that protons are positive and electrons are negative. So if the number of protons is equal to the number of electrons, then the particle is an atom, because those charges cancel out. And you can see that with particle A, the number of protons is equal to the number of electrons. And so therefore it's just lithium. It's a lithium atom with no overall charge. For particle D then, we look to the number of protons to get the identity of the element. It's got 11 protons, and that means it is sodium. So we can write down Na, but we need to check whether it has a charge, so whether it's an ion. And in this case, our number of protons is not equal to the number of electrons. We've got 11 protons and only 10 electrons. So you can think of this as there's one more proton than electron, and therefore it has a positive charge. Or, if you want, you can write out your number of protons and your number of electrons. So there are 11 protons, so I can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 protons and 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Where there's an electron for a proton, they will cancel out. So we can cancel out all of these. And we can see that we're left with one positive proton. So the formula is Na+. Then finally, for particle E, we can get its identity from the number of protons. 17 protons, that means it's going to be chlorine. Then we need to check whether it's an atom or an ion. And again, we can see that there's a different number of protons than electrons, so it must be an ion. In this case, there's one more negative electron than there is positive protons, and that means my charge is going to be negative. Again, you can write out all your pluses and minuses to see which cancel out. But here you can see there's one more E than P. Each electron has a negative charge, and so that means our charge is 1-. So you had to be careful there. Read the question carefully. It says they may be atoms or ions. In this case, D and E were ions, and so you had to identify their charge. Question number 2 was about solubility curves. In the first part of the question, I asked you to plot the points of potassium chloride, a separate salt, on the graph. If you're asked to plot points on a graph, always do this in pencil and be very, very careful about the scale. That's where people lost marks here. So the first thing you need to do is identify the scale, particularly on the y-axis. By having a look at our scale here, we can see that 2 of the bigger squares is equal to 20. So that means 10 would be here, which means that each one of these individual squares is worth 2. And that's where people lost marks. So each of these goes up in 2. So that's 2, 4, 6, 8, 10. So the first solubility value was at 0 degrees C, and the value was 28. So if each square is worth 2, that means that our point is there. And the centre, you should plot it with x's, and the centre of your x should always be on the exact point. And just be really careful with this. I think some people did this very quickly and very messily, and it meant that they lost marks. The marks go for how many points you have plotted correctly. If they've given you the points, given you the scale, they expect it to be plotted exactly accurately. The other thing is always do this in pencil. It means if you make a mistake, you can rub it out, but also graph work should always be done in a pencil. So next one was at 10 degrees C, so I go across to temperature of 10 and I go up to 31. Again, because each of my tiny squares is worth 2, that means 31 is going to be halfway in between 30 and 32. And again, it needs to be exactly halfway in between. Continue plotting these, and you should get the following points. If you lost marks, I marked which ones were plotted correctly. Please replot these, and perhaps in pencil this time so that you can see them. The danger of pencil is sometimes that your points are too light. So just be careful about that as well, that you have done them darkly enough for the examiner to see them, and also because these papers are marked by on computer screens, so it needs to be dark enough for the scanner to pick it up. Okay, now it did say plot a solubility curve, but sometimes solubility curves can be a straight line. Essentially what you're doing is drawing a line of best fit. Sometimes that's a straight line which you'll draw with a ruler, sometimes it's a curve. You can see that with the graph of potassium nitrate that's already been plotted, it's obvious that that's not a straight line. If I had taken a ruler with that one, it would have been a line something like this, which obviously doesn't fit the points of potassium nitrate. But how you should check is take a ruler and try to fit it through your points. If it fits through your points, then draw, or most of your points, then draw it with a ruler. If it doesn't, and it seems like a lot of the points are off the line, and particularly if they're curving up, then draw it freehand and draw it as a curve. But it's quite obvious that these points are in a nice straight line, and so this should have been drawn with a ruler. And so you need to take a ruler and you need to join your points. And you can see that a straight line goes nicely through most of the points. So just use your judgment with this. Again, take a ruler and see if it goes through most of the points. Everybody lost at least one mark in this question. That was because they didn't use a ruler. And it may have been that word curve that put you off. But just be aware of that sometimes your solubility curve is going to be a straight line, which you need to draw with a ruler. That affects your points for the next question, but we'll go through the next question using this graph. So part B asks the question to describe and compare the trends in solubility for potassium nitrate and potassium chloride. What we can see from looking at them is that as the temperature increases, the solubility also increases for both of these salts. And a lot of people maybe lost a mark here about how they worded their answer. And when describing a trend from a graph, that's always how you should write your answer. As something is increased, so as whatever is on your x-axis increases. So if we write the general answer here, as x increases, and then whatever's on your y-axis either increases or decreases. Okay, that's your general answer for how you describe a trend in a graph. In this case, what's on our x-axis is temperature. So we want to write as temperature increases. And then we want to write what's on our y-axis, which is solubility. The solubility of both our potassium nitrate and our potassium chloride. And we ask ourselves, does it increase or decrease with temperature? And we can see from our graphs that they clearly increase. The graphs go up. So that is how the solubility curves of the two salts are similar. They both increase as temperature increases. But then when we want to compare them, obviously they are a different shape. And what we can see from the graphs is that the solubility of potassium nitrate is much more affected by temperature than potassium chloride. So I wanted to say something along the lines of the solubility of potassium nitrate increases to a much greater degree with temperature than potassium chloride. How the mark scheme puts it is that the solubility of potassium nitrate increases more rapidly or to a greater extent. You could write that, or you could write the opposite of it. So essentially the increase in potassium chloride is steady. So it goes up in the same amount each time, or roughly the same amount each time. or it increases more slightly. It only goes up a solubility of 2 or 3 grams every 10 degrees C. Or potassium chloride increases steadily. Or slightly. Part C asks the question, at what temperature do both salts have the same solubility? And depending how you drew your graph, you may or may not have got an accurate answer for this. If you plot your points correctly and draw your straight line, you should have got an answer of around 22. Now again, my graph won't be completely accurate because I've drawn it using this app, but we're looking at for the point at which the two lines cross, and you can see that it's roughly at 22 degrees Celsius, and that's the mark scheme answer here. They took plus or minus half a degree, but what they were looking for, if you've drawn it accurately, it should come out as 22 degrees C, but you're looking for the temperature at which the two lines cross. The first part of Part D asks, what is the solubility of potassium nitrate in 100 grams of water at 43 degrees C? Again, you had to be careful about which curve you used here. Potassium nitrate is the one that they drew. And again, then you need to be careful about the scale. So look at the x-axis, 43 degrees C. In this case, in the x-axis, each square, you can see, is worth 1 degree Celsius. So 43 degrees is here. So we draw a straight line using a ruler up from 43 degrees until it meets the line of the potassium nitrate solubility curve. Then again, using a ruler, draw a straight line across to get your solubility value. And again, we need to be careful about the scale, remembering that on our y-axis, each little square is worth 2. And so that means our solubility value is going to be 68 grams per 100 grams of water. You had to include your unit, and your unit should have been easy because you're given it on the y-axis. You can't fully see it on this screen, but on your y-axis, if you look at your paper, you're given the unit of grams per 100 grams of water. You should also know that solubility has those units. The second part of Part D asks for the difference in solubility in 100 grams of water at 43 degrees C of the two salts of potassium nitrate and potassium chloride. So we've just found out that for potassium nitrate, the solubility at 43 degrees C was 68 grams per 100 grams of water. We then need to look at our graph and find out the solubility value of potassium chloride. Again, whether or not you've plotted your line correctly will affect your accuracy of this question. So we need to go up from 43 degrees to get our solubility of potassium chloride. If we then draw a line across to our solubility value, we should find that our solubility of potassium chloride is 40 grams per 100 grams of water. To find the difference in solubility, we simply take the two values away from each other. So 68 minus 40 is 28 grams. You can either write your units as grams or grams per 100 grams of water, but you need a unit. If you didn't write a unit, then you will have lost a mark. Final thing to check in this sort of question is that it's for 100 grams of water, because obviously your solubility values on the y-axis are grams per 100 grams of water. If this value was for 200 grams of water, you would have to times your final answer by 2. But in this case, it's just for 100 grams of water. And so we can leave it at this answer. Your final answer is just 28 grams or 28 grams per 100 grams of water. Part E is the mass of crystals formed on cooling type of question. And again, as we discussed in class, the way to do this is step by step. First of all, you want to write down the solubility at the higher temperature. So the solubility at 56 degrees C is equal to, And for this type of question where there's two curves on the same graph, we need to be careful about which salt it's asking for. So it's asking for the solubility of potassium nitrate at 56 degrees C. So again, being careful about our scale, we go up from 56 degrees C. Using your ruler, draw a straight line up to the curve. And then draw a straight line across to the y-axis to work out your solubility. And you can see, remembering that your y-axis goes up in 2s, that your solubility at 56 degrees C is 96 grams per 100 grams of water. And then you write down your solubility at the lower temperature, which in this case is 25 degrees C. So again, go to 25 degrees C, go up to the curve, being careful that you get the correct one, and go across, and you find that the solubility at 25 degrees C is 38 grams per 100 grams of water. We can then find the mass of crystals formed on cooling 100 grams of water by taking these two values away from each other. The mass of crystals formed on cooling is going to be 96 minus 38, which equals 58 grams. At this stage, you need to check your mass of water. And in this case, we have 100 grams of water. So in this case, we don't have to multiply or divide by any value. If it was 50 grams of water, we'd divide this value by 2. If it was 1,000 grams of water, we'd times it by 10. But here, it's just for 100 grams of water. And so this is our final answer, 58 grams. And again, you get a mark for your units, so make sure you include those. And really, when you're ever giving an answer that is a value, a number, there should be units afterwards. Because if you hadn't put the units here and your answer was just 58, that could be 58 anything, could be 58 miles, 58 kilometres, 58 kilograms, but no, our answer is 58 grams. The next question was your extended question, your 6-mark question, and it was on ionic solids. The question even told you that sodium chloride has an ionic crystal lattice structure, so it gives you the structure of this compound. And you can see your diagram there, which shows you the structure of sodium chlorides, and it's very similar to the model that I have in class. And you can imagine that these green ions are your chloride ions, and the white ones are your positive sodium ions. So these charges, these ions, are right throughout the lattice structure. And we have to think to ourselves, what is an ionic bond? Well, an ionic bond is the electrostatic attraction between oppositely charged ions. Okay, so that's what an ionic bond is. So what is holding this structure together is the attraction between my negative chloride ion and my positive sodium ion. Positive sodium ion and my negative chloride ion. Because they're oppositely charged, they are attracted to each other. Now the structure of it is how that continues on a larger scale. So this attraction continues right throughout the lattice. So we've got ions that go in all directions, and these ionic bonds go in all directions. And that has an effect on the physical properties of our sodium chloride. And we have to think for this question, how does the structure affect its properties? Well, the first property you should know of an ionic compound is that it has a high melting point. And that is something that you should be familiar with. But you should also be familiar with the explanation. And the reason it is a high melting point comes as a result if we have to put a lot of energy in to break something apart. And you can see from your structure here above that this lattice structure continues on and on and on. And in order to melt this down, I have to separate all these individual ions. I have to break them apart. So I have to put a lot of energy in to break them apart. And the reason that is because the attraction between the ions is very strong. And those individual bonds are very strong, but also those bonds go in all directions. So essentially, to start off the question, you should be able to recall that they have a high melting point. And that is because there are strong forces of attraction between the ions, or between the oppositely charged ions, and these strong ionic bonds go in all directions, and therefore a lot of energy is required to break these bonds. And this is something that we went over quite a lot when we were studying this topic, and we revised it when we came back in January. And so it's something you need to be familiar with. You need to be familiar with the various properties of the different structures, and also the explanation of why they have these properties. So for the first mark, for the first physical property, you would have got a mark for saying that it has a high melting point. And actually they were just looking for this idea of the strong forces of attraction. But it's good to go on and explain it fully. You were asked in the question to predict and explain. So therefore you've predicted and predicted the physical property, which is high melting point, and you've explained it by the strong forces of attraction. Because it's got a high melting point, sodium chloride is also a solid, and you would have got a mark for that as well. Second general property we looked at was electrical conductivity. And you need to remember with ionic compounds, and you needed to state this explicitly. Some people talked about it conducting electricity or not being able to conduct electricity. But you need to remember that ionic compounds can conduct electricity when molten or in solution, but not as a solid. So the first thing you could say there is cannot conduct electricity as a solid. And then think to explain that. Why is that? Well, if we look back up at the diagram, we can see that yes, we have charged particles, and in order for something to conduct electricity, they need to have charged particles that are free to move and carry the charge. So I look at my diagram and I see, do I have charged particles? Well, yes, I do. I have my negative ions and I have my positive ions. They are charged, and so they're charged particles. Okay, but the second criteria that they have to be is they have to be free to move and carry the charge. Right now you can see from this diagram that they're not free to move and carry the charge. Yes, they are charged, but they're not free to move. And so we need to explain that in our explanation. They cannot conduct electricity as a solid because the ions are not free to move and carry the charge. And that is because they are in a fixed position within the lattice. But as we said above, when we melt ionic compounds, we are breaking them apart. And so if we look at the diagram above, what we're essentially doing is we are breaking this fixed structure into its individual ions. So the sodium ions and the chloride ions, they will be separated out when melted. And so now when they are molten or melted, the ions are free to move and carry the charge, and so it can conduct electricity. We have charged particles that are free to move, so they fit both the criteria that we said over here. And the same applies for when it's in solution, because when it's in solution, the water molecules, if we can imagine the water molecules here, they come in and they bring the ions away from the lattice structure. So the same applies for when it's in solution. So again, we can say something in our answer here, that it can conduct electricity when molten or in solution, as the ions are free to move and carry charge. And one thing I want to say on that is you have to be particular about the charged particle that you're involving here, because a lot of people talked about the electrons not being free to move and carry the charge, and in ionic compounds it's always the ions or the charged particles. The delocalized electrons are to do with metallic compounds or graphite, but with ionic compounds the charged particles are the ions, the positive and the negative ions, so be careful about how you phrase that. Other things that you could have written are that ionic compounds are soluble in water, or that they are brittle, which just means that we can break them apart. So there you have a number of physical properties, and for each of them, and particularly high melting points, and for the electrical conductivity, you have an explanation as well. And those explanations should go alongside the physical property that you're mentioning. Again, something that we went over a lot, that's in your notes in very condensed bullet points. So if that's something you struggled with, it's important to go back to your structures booklet and learn the different properties of your different structures. Question 4 was from your acids, bases and salts topic, and it was looking particularly at the reaction of metal carbonates and acids. And you should be familiar with your general equation for this, the fact that when metal carbonates react with acids, you get a salt, you get water, and you get carbon dioxide. That's your general equation for the reaction between metal carbonates and acids. And as soon as you see these types of questions, you should write out that general equation, especially if you're asked to write a balanced symbol equation and you know that your different side products. And that would have really helped you with this question if you'd written that general equation. So the name of our salt we know comes from our acids and our metal carbonate. First part of the name comes from the metal, second part of the name comes from the acid, and that also determines the anion in our salt that we'll look at now. So we know that when we use hydrochloric acid, the second part of our name of our salts turns to chloride. First part of the name comes from the metal and that stays the same. So the name of this salt is going to be calcium from the metal carbonate, and chloride because we used hydrochloric acid, calcium chloride. Once you've got that name, it's easier to see the anion in the salt. The cation is going to be from our metal, which is calcium, and we can see that here in our first box. Has already been done for us. The anion comes from the second part of the name of the salt, and in this case it's chloride. So chloride is just a simple anion of chlorine. We know that chlorine is Cl, and then if you look at your group number, you can see that chlorine is in group 7, and so it forms ions with a charge of 1-. So it should be just Cl-. Now a number of people wrote that it was Cl2-, thinking that chlorine has to be diatomic, but when it's part of a compound it is no longer diatomic, so that would have been incorrect to do it that way. Another way to see this is to look at your formula of your salt produce. It's CaCl2. We have been told that calcium is Ca2+. We can see from the 2 that we have 2 chloride ions. And so to cancel out the charge of calcium, each of those must have 1 negative charge each. So actually we have a Cl minus and then a second Cl minus, and those charges cancel out. So that's where we get our formula for the anion in the salt. The next example of the salt, we can see from the anion that it's sodium sulfate. SO42- is sulfate. Sulfate salts come from sulfuric acid. So it's sulfuric acid that we wanted to write in that box. In order to get the formula of the salt produced, we need to do our swap and drop, and we can see that easily from our ions. Cation is Na+, which means that sodium has a valency of 1. The anion is SO4 2-, which means that the sulfate ion has a valency of 2. When we swap and drop that, we get the formula of the salt to be Na2SO4. The third row then looks at a new salt. You can see from its formula that it's copper sulfate. Cu is copper. That means we must have started with copper carbonate, and most people got that. Again, you can see from the formula that you've got sulfate, or from the acid, sulfuric, therefore we would produce copper sulfate, which means the anion, as above, is SO4 2-. The next one you might not be just as familiar with, but you had all the information that you needed. Firstly, the metal carbonate is magnesium, which means the cation is going to be the magnesium cation, which is Mg2+, because magnesium is in group 2, so it forms an ion of 2+. Then if you weren't sure about the anion, well, nitric acid actually produces salts called nitrate salts. So the name of this salt would be magnesium nitrate. But if you weren't sure about that, you should be able to see it from the formula of the salt. In the brackets here we've got NO3. And if you look to the back of your periodic table, you can see that nitrate is NO3 with a charge of minus. Part B was asking about colour changes. And says that one of the reactions in the table above involves a colour change, and that was this reaction here of copper carbonate and sulfuric acid. You needed to remember, and it told you in the question, that it was a metal carbonate. So really we are looking at the reaction between copper carbonate and sulfuric acid. Again, if you'd written your general equation, you'd know that we produce a salt, which in this case is copper sulfate. We'd produce water, and we'd produce carbon dioxide. Okay, so the first part of the question asks you the metal carbonate colour. So I'm asking myself, what colour is copper carbonate? And you need to remember that the colour of copper carbonate is green. The colour of the salt solution produced is the colour of this, copper sulfate, and you should know that copper sulfate is blue. So as we talked about at the time, you may be asked for the colour change in the solution, which would be the colour change of sulfuric acid, which is colourless, to the colour of copper sulfate, which is blue. So it'd be colourless to blue, but it specifically asks you here, what is the colour of the metal carbonate? And then what is the colour of the salt solution? So that colour change was green to blue. The next part of the question follows on from that, and again, if you've written your general equation, that should help. So let's write it again here in case you didn't get it at the top. It is that a metal carbonate plus acid gives you a salt plus water plus carbon dioxide. So therefore, your gas is carbon dioxide. And you needed to be careful there that you read that the table said metal carbonates rather than just metals with acid. And if you read the question carefully at the start, it says the table gives information about the salts formed when metal carbonates react with acid. So a lot of people talked about hydrogen here, but the correct answer was carbon dioxide was the gas. And again, if you were talking about hydrogen, you would have been talking about the POP test, which would not be correct. The test for carbon dioxide is that you pass the gas through lime water. That's important to say. Some people were talking about blowing into carbon dioxide. Well, that's really to test the gas that you exhale, to test that that contains carbon dioxide. But we're not testing the gas that we exhale. We're trying to test the gas that we produce in this reaction. So what you need to say is pass the gas through lime water, and that's where you got your first mark by saying lime water. And then the second mark will be for saying, really you just needed to say that it turns milky. The best way to do that is say that lime water changes from colourless to milky. But the important thing is about it turning milky. Okay, so that is the test for carbon dioxide, and you need to know that. You pass the gas that you're testing through lime water, and that the lime water turns from colourless to milky. Question 5 is about the melting point of different metals, and mostly revolves around interpretation of the graph below, which we'll have a look at in a second. But the first part of the question asks you what was meant by the term melting point. And if you ever come across a definition that you're not sure about, think about how you would apply it in real life, or what its real life application might be. So think, well, first of all, what is the melting point of water or ice? The melting point of ice is 0 degrees C. Well, what does that mean? That means that ice melts at 0 degrees C. What is 0 degrees C? Well, it's a temperature. 0 degrees C is the temperature at which ice melts. But saying that ice melts at that temperature is not really a sufficient definition, because it's asking you what is the definition of melting point. So if you didn't know what melting was, then you wouldn't really understand that definition of it's the temperature at which it melts at. So what is melting? Well, melting is the change from solid to liquid. So by thinking of a real life application, I've built myself a definition. It's the temperature at which a solid changes into a liquid. So your definition of melting point is the temperature at which a solid changes to a liquid. The next part of the question asks you to interpret this graph, and it's worth taking some time to try and make sense of it or interpret it before you even start answering the questions. So if you think about the white box is when it is solid, and there's a transition between the white and the grey block. The white and the grey block is when it changes from a solid to a liquid, and so that is going to be your melting point. The black line from where it goes into a white block, the solid, into the grey block, a liquid, is going to be the melting point. And the grey block gives the temperature range over which it is a liquid. So if you look at the top of the grey box, in the case of aluminium, it's at 2500 degrees. That's when it stops being a liquid. At a temperature higher than that, if it's no longer a liquid, then it must be a gas. And so therefore, that temperature is the boiling point. So anything above this, aluminium is going to be a gas. So at 4000 degrees, it's going to be a gas. At 5000 degrees, it's going to be a gas. So now we are in a better position to answer the following questions. The first question says, which metal in the table has the lowest boiling point? Boiling point is a temperature at which a liquid changes into a gas. So essentially, as we said with aluminium, it's the top of this grey box. So at the end of the grey box. So we're looking for the metal for which the top of the grey box is the lowest. And a lot of people said cadmium for this question, but you can see that there's one lower than that, and that is of mercury. The top of the grey box, which is when mercury finishes being a liquid, any temperature higher than that, it's a gas. And so you can see that it is mercury, has the lowest boiling point. Second part of the question asks which has the highest melting point. The melting point is the temperature at which it changes from a solid to a liquid. So when the white box goes into the grey box. And if you compare the different metals, the one with the highest melting point is that of chromium, which is a melting point of 1900 degrees. The next question, part 3, it says, from the data in the table, in what way are gold and aluminium very similar? Now this was a difficult question to see. You had to really look at the graph. So we're looking at gold and we're looking at aluminium. And what actually they wanted you to see was essentially that the height of your grey boxes are the same. We'll talk about what that means in a second. So if you look at the difference between the melting point and the boiling point of gold, so it's just below 2,900 degrees C for the boiling point, and just above 1,000 degrees C for the melting point. So essentially gold is a liquid between 1,000 and 2,900 degrees C. So if we take 2,900 and we take away 1,000 from it, we get 1,900 degrees. That means it's a liquid over 1,900 degrees C. Then if we look at aluminium, its boiling point is 2,500 and its melting point is 600 degrees C. If we take those two away from each other, again we get 1,900 degrees C. And so both of them are liquids over a similar temperature range. And so you could put that in two different ways. You could say that the two metals are liquids over a similar temperature range. Or you could say that they have a different, or a similar difference between melting and boiling points. So again, that was difficult to see from the graph, but you need to really study the graph carefully and understand what it's about before answering that. This next question was answered well, and it asks you to describe similarities and differences between the relative ductility and malleability of these 7 metals. The only thing that was wrong with the answering of this question was either not making distinct points or just the wording of it. So notice how it goes from the most ductile to the least ductile, and it goes from the most malleable to the least malleable. Some people talked about iron not being malleable, but that's not true. Iron is still malleable, but it is the least malleable out of these 7 metals. So it's comparing the malleability of the 7 metals. So it's not as malleable as gold, say for example, but it is still malleable. So just be careful about how you word your answers. So your question was worth 3 marks, and so they were looking for 3 distinct points. The first thing you could have noticed is that gold was the most ductile and also the most malleable. That could be 1 point. A separate point could be that copper has the same level of ductility as it has malleability. It's third in both of those lists. That will be a separate point. A third point, which a lot of people picked up on, was that iron was high up in the ductility list, but it has a low malleability. So iron has a high ductility in comparison, but a low malleability. Other points you could have noted were that the other metals had similar levels in both. So for example there, you've got zinc is very similar in ductility as it is in malleability. So they were looking for 3 distinctive points there, and all again reading from that table of information. The next question, however, is something that you should be familiar with, and again was quite poorly answered. And for this, you need to think about the structure of metals. That's something you need to be familiar with in order to answer this question. Think about how metals and how they are arranged in positive ions arranged in layers. Those are your positive metal ions, are arranged in nice regular layers, and they are surrounded by delocalized electrons. So metals bond by losing their outer electrons, and so the metal ion exists as a positive metal ion, and they're surrounded by then the electrons that they have lost from their outer shell. And we call this a sea of delocalized electrons because these electrons are constantly moving, and so they form kind of an average charge that we call a sea of delocalized electrons. They're constantly moving around. They're free to move and carry, that's how they can carry charge. But that wasn't relevant for this question. Some people were talking about electrons moving and carrying charge, but that's not what it's talking about. It's asking you to explain why metals are malleable and ductile. So the first thing you wanted to talk about was the structure of metals. So metals exist as a regular arrangement of metal ions arranged in rows, or something about the metal ions being arranged in regular rows. And they are surrounded by a sea of delocalized electrons. Okay, so you're first of all describing the structure. Then you want to say why that means it can be malleable and ductile. Think about what malleable means, that it can be hammered into shape. Ductile means that it can be stretched into wires. So it'd be worth writing that above. Malleable means it can be hammered into shape. Ductile means it can be stretched or drawn into wires. Okay, so now I want to think about how my structure can help that. Well, think about what metallic bonding is. Metallic bonding is the attraction between these positive metal ions and the delocalized electrons. The attraction between oppositely charged particles, positive metal ions and the negative electrons. What I can do is I can pull this layer of metal ions across. So essentially pulling that across to the next row. So stretching it out, this would be describing how it's ductile. But it can still maintain that attraction between the positive metal ions and the negative electrons because the negative electrons are free to move. So essentially I'm pulling the metal ions over each other, over the layers. I'm sliding the layers past each other, but I'm still maintaining that bonding because the electrons can move with the ions. So as I slide the layers across each other, the electrons can move with it and still maintain that bonding. So the layers can slide over one another, without disrupting the bonding. So in order to answer that question successfully, you need to have that idea of metallic structure in your head. This idea here. And also what metallic bonding is, that it's the attraction between these positive metal ions and these negative electrons. And then how, when you pull these layers of metal ions over each other, why the bonding can still be maintained. And that is because the bonding is the attraction between the positive ions and the negative electrons. And the electrons, because they're free to move, they can move with the ions as they slide over each other and still maintain that bonding. So get that answer into your head, because it's going to be worth 3 or 4 marks if it comes up. The next question was about covalent bonding, and the first question said, what do you understand by the term covalent bond? And when it asks what a particular bond is, you need to be thinking, what is holding the atoms or the ions together? That's what a bond is. It's what actually holds the atoms or the ions together. So people were talking about a non-metal and a non-metal atom, which is what covalent bonding is between, but the bond is actually what holds them together. And we talked about this a lot of times, that a covalent bond is one shared pair of electrons. If you think about the covalent bond between hydrogen atoms, so to make H2, is both hydrogens use their single electron and they share them. And the covalent bond, what actually is holding these 2 hydrogen atoms together, is this thing right here in the overlap. And that is one shared pair of electrons. So that's what they were looking for A. For part B, it asks for the dot and cross diagram for carbon dioxide. If you're not familiar with this, please learn this. Practice drawing it over and over again until you're confident with it. If you're not sure, if you haven't learned it, look at the formula of it. And it says, show the outer electrons only. Please be careful about that. Some people lost marks for including the inner electrons as well. So, carbon dioxide, CO2. You can tell from that, I'm going to have 1 carbon and 2 oxygens. So the first thing to do, if you're not sure, if you haven't learnt the dot and cross diagram for this, which I would advise that you do, because you're more than likely going to get 2 or 3 of these dot or cross diagrams. There's 9 structures that you need to learn, and the list of those is in your bonding booklet. So for carbon, I need to think how many electrons are in its outer shell, and in order to get that, I look at my periodic table. I see that carbon is in group 4, which means that it has 4 electrons in its outer shell. And I put it at north, east, south and west. Oxygen then is group 6, which means that it has 6 electrons in its outer shell. Doesn't matter how many electrons it has in total, but just that it has 6 in its outer shell. So 1, 2, 3, 4, 5, 6. And I have 2 oxygen atoms, so I'm just going to draw the second one as well. North, east, south and west, and then back round at north and east. And with covalent bonding, it's the unpaired electrons that are involved in bonding. It might be worth writing that down. Unpaired electrons involved in bonding. That means I know that this electron, this electron, this electron and this electron are going to be involved in bonding. So they're going to end up in the overlap of covalent bonding. This electron and this electron are involved, and this electron and this electron are involved in bonding. So if I draw what they produce on the right hand side, what happens is these 2 electrons pair up with the 2 unpaired electrons in this oxygen, and these 2 electrons pair up with these two unpaired electrons in this oxygen. So what we find is that we have a carbon in the middle with an oxygen on either side. And we've got two of our oxygen electrons in here, two of our oxygen electrons here, two of our carbon electrons in this overlap, and two of our carbon electrons in this overlap. But what you need to make sure to do is to include the electrons that were already paired up. So each oxygen has two pairs of electrons that were already paired up, and they go on the outside of each oxygen. You need to remember about those, and those are our lone pairs. They're not involved in the bonding, so we call them lone pairs. And a good thing to do at the end of each of these dot and cross diagrams is check that each atom has 8 electrons in its outer shell. So if you count round each atom, so first of all this oxygen, it has 1, 2, 3, 4, and then 4 more in the overlap, so that's 8 electrons. The carbon has 4 in each overlap, so it has 8 electrons in its outer shell, as does the oxygen on the other side. So this should be your dot and cross diagram for carbon dioxide. So please make sure you learn that and are familiar with how you draw that. With ammonia, again, if you're not sure of what the dot and cross diagram looks like, look at the formula. I can see that I've got 1 nitrogen and 3 hydrogens. So nitrogen first of all. Nitrogen is in group 5, and so it has 5 electrons in its outer shell. 1, 2, 3, 4, 5. Hydrogen just has 1 electron, and we have 3 of those. Hydrogen only has 1 to share, and the nitrogen, remember we said the unpaired electrons are involved in bonding. So we're going to see a hydrogen coming in here, we're going to see a hydrogen coming in here, and we're going to see a hydrogen coming in here. And so we end up with ammonia. The dot and cross diagram looks like this, with 3 hydrogens overlapping at each position, where the nitrogen had unpaired electrons. So again, the unpaired electrons pair up. And don't forget about nitrogen's original pair of electrons that was already paired up, this here. And actually it turns out that's our answer to part 3. That is the lone pair, the ones that are not involved in bonding. Question 7 was actually one that we'd come across in our winter exam, so don't want to spend too much time on that. So it's something you should have been familiar with, and make sure you do go through your past tracking tests, as that is good revision to go through those past paper questions. First question asks you to describe the trend in physical state and the colour. So where people lost marks here was they didn't specifically talk about physical state, they maybe talked about the trend in melting point, but it specifically says physical state. And then some people forgot the colour. So again, make sure you're reading the question carefully. I think people are rushing into the reading of questions and missing what they're being asked to do. So trend in the physical state, as you move down the group, you can see that it moves from gas to liquid and then to solid. And that's all you need to say, that as you move down the group, and some people didn't write that, and I did give you the mark, but you should really say, as you move down the group, physical state changes from gas to liquid to solid. And in fact, you didn't even need to say the to liquid bit in the middle, as long as you said gas to solid. But then the second mark is for saying the trend in the colour, and you needed to say that colour darkens as you descend the group, or as you go down the group. That was for the second mark. Okay, second part says, explain why all the halogens form ions with a charge of -1. This is going back to your periodic trends topic and explaining why elements in the same group have similar chemical properties and why they all form ions with the same charge. If you think about halogens, they're all group 7. So even if we look at fluorine here, it has 9 electrons in total, 2 in the first shell and 7 in the next shell. So we need to think, when it's forming an ion, what does it do? Well, when it's forming an ion, it is aiming to get a full outer shell. So that's actually one of your marks here in this question. It's aiming to get a full outer shell. And so what does it need to do to get a full outer shell? Well, it needs to gain 1 electron. So if I put that in as a blue dot to represent that, it has gained that electron. Once it has gained an electron has a negative charge. So for every electron you gain a negative charge. Okay, so you wanted to say something like group 7 halogens, because they specifically say halogens in the question, all have 7 electrons in their outer shell. Therefore, they need to gain 1 electron and I would use the number 1 there instead of they need to gain an electron. It's just specific that it's 1 and not 2 electrons. They need to gain 1 electron to achieve a full outer shell. That's your fullest explanation there. They were looking for sort of 2 out of those 3 points, maybe that they have 7 electrons in their outer shell. This idea of them gaining 1 electron, that's a point you must include. And that's kind of obvious from a charge of -1. How do I get a charge of -1? Well, it's if I've got 1 extra electron, if I've gained an electron. Next question talks about astatine, the 5th member of the halogens, asks you to predict the property. So if you look at the table above, physical state at room temperature, well, if it's below iodine, then it must be a solid, because we move from a gas to a liquid to a solid, as we said in the first part of the question. The colour, well, you can see that the colour intensity increases, it gets darker, and therefore the colour is going to be black or very dark black. Toxicity for all of the elements, all of the halogens, if you look in the table above, is high, so it's going to be high for astatine as well. Formula of the ion, well, you need to look at the symbol for that element. Astatine is At, and the charge, like all of the other halogens, is minus. Formula of the molecule then, again, just as all the other halogens, is diatomic, so it's going to be At2. Next question, you have to be careful about your spelling here, because we know that when a metal reacts with a non-metal, the metal name stays the same. So our metal is sodium, and the non-metal changes its ending to IDE. So from INE to IDE. So we write ASTAT, and instead of INE, it's IDE. A bit like fluorine changes to fluoride, or chlorine changes to chloride. The last question is an electrolysis question, and specifically about the electrolysis to achieve or to obtain aluminium from its ore. Aluminium ore is mainly made up of aluminium oxide. Aluminium oxide, if you do your swap and drop, you get a formula of Al2O3. So what we're trying to achieve through electrolysis is the splitting up of this compound into aluminium and oxygen. And we'll look at how that is achieved in a second. The first question is, what is the name of the aluminium ore? Well, that is called bauxite. The aluminium ore is called bauxite, and that's something you need to know. Part B is write an equation for it to show what happens at the cathode. Well, there's a couple of ways you can remember this. Cathode is the negative electrode. So what is attracted to the negative electrode? positive ions, which are called cations. The cation is always the metal ion, and in this case the metal ion is aluminium. So we're going to be forming aluminium at the cathode, and so we need to write a half equation to show how aluminium is formed. The other way to remember it is just that the metal is always formed at the cathode. It's probably the simpler way of doing it. So what is my half equation? Well, think about what we're doing. We're trying to produce aluminium. So aluminium is going to be on the right hand side of our equation. But aluminium element with no overall charge is formed from its ion. So as in aluminium oxide, aluminium is Al3+. How I get that charge of 3+ is I simply look at my periodic table and notice that all group 3 elements form a charge of 3+. So Al3+, how do I get that to aluminium? Well, I've got 3 positive charges, and how I'm going to get to overall no charge is either gain or lose electrons. Electrons have a negative charge, so I need to gain a total of 3 electrons to get to an overall charge of 0. Each electron I add almost takes off one of those positive charges. And the way you can think of that is that right now, aluminium as an ion has 3 more protons than electrons. So in order to balance that out, I need 3 more electrons so that I have an equal number of protons and electrons. Next part of the question is explained clearly in your notes, but it says, why do the anodes need replaced periodically during this process? First thing I need to think about is what my anodes are made of, and that actually is your first mark. Anodes are made out of graphite, which is carbon. So we need to say anodes are made of carbon. That's your first mark. Okay, then I need to think about what is produced at the anode. Well, if aluminium is produced at the cathode, then that must mean oxygen is produced at the anode. And you can look in your notes for a half equation for that. So that's your second mark. Oxygen is produced at the anode. So if we've got anodes made of carbon, and we've got oxygen produced at those carbon anodes, we're going to get carbon dioxide formed, and that's because it reacts because of the high temperatures used. And that actually wasn't part of this mark scheme, but we'll include this here because sometimes it is in the mark schemes. So due to the high temperatures involved, carbon reacts with the oxygen produced to form carbon dioxide. And at this point it would be good if you could include the equation, which we've written below in blue, or even write a formula equation of carbon plus oxygen giving us carbon dioxide, which is CO2. And then again, that is all you needed for the mark scheme answer. But you could write something along the lines of, therefore, the anodes will gradually wear away. Next part again was based around this industrial example of the extraction of aluminium using electrolysis from aluminium oxide. And what we learnt was that before we carry out electrolysis, we add this thing called cryolite, molten cryolite. And it reduces the cost of electrolysis. So electrolysis is very expensive because of the high temperatures involved. And that's because we have to get our we have to melt our aluminium oxide so that the ions are free to, the aluminium ions and the oxygen ions are free to move and carry charge. And it's also expensive because of the high levels of electricity that we need to use. And so how cryolite helps is it actually helps both of these factors. So first of all, we said it's expensive because we need to heat it up to a high temperature to get our aluminium oxide to melt. And so how cryolite works is that it lowers the melting point of aluminium oxide. So I don't have to heat it up to such a high temperature to get it to melt. Therefore, I don't have to apply as much energy. Therefore, it is cheaper. Just a note on that, a lot of people said lowers the melting point, but you need to say lowers the melting point of aluminium oxide. It's the aluminium oxide that I need to melt so that its ions are free to move and carry the charge. So just be specific about that. Second thing it does is it reduces the cost of electricity by increasing the conductivity of aluminium oxide. Okay, the last question was looking at two factors which should be taken into account when siting an aluminium extraction plant. That word siting just means when you're deciding where to place an electrolysis plant for extracting aluminium. There's a list of factors in your notes, and as I said at the time, you probably will never need to know all of those unless you got a 6-mark question on it, which I think is highly unlikely, but it is possible. So be familiar with those reasons. There's something you should be able to think about logically as well, and I had some good answers for this, and then some not so good answers as well. So there's a list in your notes, so do be familiar with those. But also take the time to look at some of the answers on the mark scheme. So you're thinking about things like having skilled professionals available to work at your extraction plant, good transportation links, good availability of your raw materials, so of your bauxite, your cryolite and so on. You need to think about waste disposal. You need to think about it being close to a water supply to cool down your machinery. All of those industrial implications that you need to think of in order to get one of these extraction plants up and running. So again, look at the mark scheme answers and look at your notes. So take some time to look through your paper and review the areas that you went wrong. Identify specific areas that you need to work on between now and your exam, and really put in the revision in order to improve those things.